As we begin our new section on exponential functions, we're going to start with an experiment. We're going to take any size piece of paper, you can do it with a half sheet of paper or a whole sheet of paper, and we're just going to record, we're going to fold it and record how many rectangles are formed. So when we haven't folded the paper at all, the whole piece of paper is one big rectangle. So I'm just going to record this in this quick chart that I have made. Now, after we fold the paper once, and I fold it in half once, when I open it back up, I'm going to notice that there are two rectangles now formed by my paper. When I fold my paper twice, when I open it back up, I'm going to find four rectangles. When I fold it 3 times, I end up with 8 rectangles. Okay. What's the pattern that you're noticing here? When I fold it 4 times, well, now I should end up with 16 rectangles. Notice that each time I'm multiplying by 2 to get to my next number. If I can successfully fold this paper 5 times, which is questionable, it's not very pretty, but when I unfold it, I should see that there are 32 rectangles on this paper now. Again, multiplying by 2. I don't know that I can get this thing to fold 6 times, but if I did, I should see that there would be 64 rectangles because, again, we're multiplying by 2. The key here is the pattern. We're seeing a multiplication pattern happening, and that's what we're looking for to exponential functions. Once we've recorded the data from our folding paper experiment, we're going to go to Desmos.com and we're going to graph that data. To start, I'm going to enter my first data point as an ordered pair. So 0, 1 was the first thing that we found when there's no folds, there's just one piece of paper, one box there, and that puts that point on the graph. Once that point is entered, I can go to the settings button here, and when I do that, I can convert this to a table, so that way I can add the rest of my data points. I can enter in the rest. I have 1, 2, 2, 4, 3, 9. The pattern that we observed as we were putting these in is that our pattern doubles. So each time we folded the paper again, the number of squares or rectangles that it made doubled. So even if we didn't actually get our paper to fold 6 times, we know that there should have been 64 squares by the time we were done. Now you're going to need to zoom out so that you can actually see more than just a couple of your data points. So you can use the plus and minus arrows over here. So you want to be able to see probably 4 or 5 of them. We can see when we look at this data that it's not in a straight line, so we know right off the bat that it's not linear. This one's what's called an exponential function. An exponential function is one that gets really big really fast or really small really fast. That's because we have a multiplication pattern. We notice that each time we were multiplying by 2 to get the next number in our sequence. We can also go ahead and write an equation that will model this scenario for us. Exponential equations are written as y equals your starting point or your y-intercept, which in this case was 1, times the common ratio or your pattern, so we are multiplying by 2, and then in this case your x is in the exponent. You can get that by clicking A to the squared button or by doing Control-6, which gives you your caret key. So now you'll notice on our graph here that it matches where all of our data points were. So this graph predicts what's going to keep happening. If we zoom out, we see that our points are getting continuously larger. It almost looks like the graph is totally vertical. In actuality, it's not a perfect vertical line, but it gets up there as it keeps doubling and the numbers keep getting exponentially larger. When we go to the smaller side, this line isn't actually touching 0, although it looks like it. Each time it's dividing by 2. So as we zoom in, we see that there is still space here. When we work with a larger scale, we don't see it. Each time our numbers are being divided by 2, so they're getting smaller and smaller, but they don't actually ever touch the x-axis. Another thing we need to notice is that this is an exponential growth graph. When we look left to right, this graph is increasing, so we're looking at exponential growth. Exponential decay is when we would decrease from left to right. Think of it similar to slope as far as the increasing or the decreasing part. This is an intro to exponential functions, which is what we're getting into next. So now you have a little bit of a taste of what they look like and how they work.